Testing. Okay, let me have your attention, please. Let's begin. Let me have your attention. Welcome to the University of Tennessee Nuclear Engineering Department Colloquium Program. My name is Lee Dodds, and it's my privilege to introduce today's speaker, who is Dr. Tom Sutton. He's an advisory scientist with the Knowles Atomic Power Laboratory. Tom received a BS in Nuclear Engineering from the University of Virginia in 1978, and then he journeyed to the University of Michigan for graduate studies. He received a Master of Science degree in nuclear engineering from Michigan in 1980, and then a PhD also in nuclear engineering in 1983. And then he immediately joined the Knowles Atomic Power Laboratory as a reactor physicist, and he's been there ever since, 22 years, and he has risen through the ranks, so to speak, to his current position as an advisory scientist, which is a very high position at Capitol. About a few years ago, the branch manager or the division chief left, Dick Mendelson, who's a friend of mine, and Tom took over as the leader of that group, and that group is named Nuclear Design Methods. And I know that some of our students have mentioned that we needed to have a few more highly technical colloquium presentations. Well, ladies and gentlemen, you've got one today. Tom's topic is Monte Carlo particle transport through a binary stochastic mixture using chord length sampling. So, ladies and gentlemen, please welcome Dr. Tom Sutton.
And I'm all turned on here?
It's on.
Okay, thank you. All right. Well, thank you, Professor Dodds. After having watched a number of these webcasts from Capitol, it's interesting to be on the other end of the things for a change. So, what I'm going to be talking about today, I got to give credit to the main guy. Is Tim? This work was actually mostly done by Tim Donovan. He did his work at Capitol, which is what I'll call Knowles Atomic Power Laboratory. We refer to it as Capitol. He did his work at this work at Capitol as part of his PhD thesis when he was a student at RPI. So he was a full-time employee at the lab and did his thesis work at RPI. I was on his thesis committee and was his advisor at the laboratory, and Professor Denon at RPI was his thesis advisor, and so this work really is mostly Tim's, but a little bit of me and Professor Denon as well. If Tim were here, he'd give a much better presentation, I'm sure, but I'll do the best I can. I talked to Professor Dodds a little while ago about the background of the students here, and I realized there's probably a diverse background, and maybe even more so when I include the web audience. So I thought I would just give a 2 or 3 minute discussion of Monte Carlo methods for those people in the audience who might not be real familiar with them. Monte Carlo we use at Capitol for neutron and photon transport. It's our most accurate but also our most expensive method of solving the neutron transport equation. We have other methods that we use as well. Diffusion theory, which is much more efficient but less accurate, and deterministic transport, which typically falls in between in both the accuracy and efficiency scales. Monte Carlo is a simulation method. It's not at all limited to solving the neutron transport equation. As a matter of fact, Professor Dodds and I were discussing last night about how it's used in the financial community to solve the Black-Scholes equations, which gives you the future value of stocks. And I just read an article in Forbes recently that for the first time, Monte Carlo has been approved as a device that financial analysts can use to sell stock recommendations to their customers. In the past, the financial analysts used it, but it was illegal for some reason to actually provide services to customers based on Monte Carlo, but now it's legitimate. As I mentioned, Monte Carlo is a simulation method. That's where it gets its name. It's named after the city of Monte Carlo, where all the gambling takes place. because it uses probabilistic methods. Typically in nuclear transport problems, we'll know things like the mean free path in a material. If you know the mean free path, then you know the distribution function for the distances traveled by a neutron between collisions. It's an exponential distribution, and we can use random numbers generated by the computer to sample the distance to collision from that for a particular neutron. So we simulate the sequences of events that happen to individual neutrons. And the sequence of events that happen to a particular neutron is referred to a neutron history, and I'll use that terminology during the course of this talk. I mentioned how we determine the distance the neutron moves to collision. Once it suffers a scattering collision, for example, we need to determine the new energy and direction. Typically, we have nuclear data available that gives us the probability that a neutron will scatter through a certain angle. So we use random numbers to actually choose the new angle and the new energy of the neutron post-collision. So Monte Carlo calculation is just a sequence of using random numbers to figure out what's going to happen next to a neutron. We then do this for millions of neutron histories for a typical calculation, average the result for millions of histories, and that gives us our answer. An unusual, or a thing about Monte Carlo methods that are different than other methods like diffusion theory is that results have a statistical uncertainty associated with them. The more histories you run, however, the smaller that statistical uncertainty becomes. What I'm going to talk about today is a way to handle one particular type of situation that arises in some Monte Carlo calculations. So it's kind of a specialized topic, but I think with this background you'll be able to get the gist of what I'm talking about. What I'm going to be talking about is what's called a stochastic binary mixture, and I'll explain on the next few slides exactly what that means. I'll talk about various ways of handling transport through this binary stochastic mixture. One of them is the so-called benchmark method, and it's just a brute force way of handling this issue. And I'll explain that in some detail because it gives us the exact result with which we're going to compare more efficient but less accurate methods later. I'll then talk about the stochastic transport equation and relate that to a method called chord length sampling that was an existing method when this research was undertaken, but had some limitations for the type of problem that we're interested in solving. Then I'll talk about a method called the limited chord length sampling method, which was Tim Donovan's original contribution to the field. I'll then talk about verification and testing of the limited chord length sampling method. I won't really talk too much about how the method was implemented in MC&P because I would have to show a lot of subroutines and coding, and I think that's not the purpose of this colloquium. That'd be a little too technical, I think, Lee. But I will talk about the analysis of the results that we got using a modified version of MC&P. In particular, and for those of you who don't know, MC&P is a Monte Carlo code developed at the Los Alamos National Lab. In particular, I'll talk about a sphere problem that we looked at that we invented ourselves and were able to solve using a variety of techniques to compare accuracy. And then I'll apply the method to a high-temperature gas reactor unit fuel cell problem that someone else had analyzed in the past, someone named Johnson, and I'll talk about his analysis, how he treated the effects that we're trying to get at today, and then how this new methodology seems to give a better result with less computational effort. All right, so what's a stochastic mixture? It's two or more randomly arranged immiscible materials. And show you on here. These gray areas that I've circled are one of the materials. Typically you have a matrix material, which is everything that, the areas that aren't circled, the yellow material, and then the gray material is some immiscible material that's in chunks inside the matrix material. I'll give you some specific examples. concrete is an excellent example that most people can visualize. You can think of the gray chunks as the gravel in concrete, and the yellow matrix material is the cement that surrounds the gravel. An example that's more pertinent to nuclear applications is boral. In that case, the gray particles would represent boron, and the yellow material would represent an aluminum matrix. So boral is used in criticality safety applications and shielding applications. It's a very absorbing metal. I've listed some other examples there. The HTGR, high temperature gas reactor pebble, is one we're going to look at in more detail later on, but two-phase water is another problem that's very pertinent to nuclear reactors. Fractured rock and bone and lung are things interested to oil well loggers and medical physicists as well. We're going to concentrate on a special case of the stochastic mixture, and that's the binary stochastic mixture, in which there are just two materials. The method, however, is generalizable to any number of materials, but we've only looked at two materials so far. Okay, so the particular reference problem we're going to look at is a binary mixture, two materials, but we're going to further limit it. The chunk material are going to be spheres. They're going to be uniform diameter spheres, randomly mixed in some matrix material. And just for ease of reference, we'll call the material that the spheres are made out of material 0, and the material that's surrounding matrix material 1. We put constraints on the problem so we can really model physical reality. The spheres aren't allowed to overlap each other, nor are they allowed to overlap the boundary of the problem. Even though this is a special case, it can represent many real problems, and the HTGR pebble is one that we'll go into some detail later. And the question is that we're trying to answer: how can you solve for quantities of interest, average fluxes, reaction rates, and so forth, when we don't even really know the material boundaries explicitly? And I'm going to show you on the next slide various ways that people have sought to do that. The simplest method is the atomic mix method, and that's just what we call simple homogenization. It's like you took the two materials, threw it all in a big blender, pulverized everything until they were individual atoms, and made one homogeneous uniform material, and did your analysis on that material instead of the real material that's in discrete immiscible chunks. Turns out that doesn't work very well, and I'll show you an example of that later on. Effective homogenization is essentially the same thing, but people apply self-shielding factors to one or more of the materials in order to account for the fact that in reality the materials are in these discrete chunks. The difficulty here, of course, is how do you compute those self-shielding factors, and they are difficult to compute accurately, and so this method isn't very popular either. We'll talk about the lattice method. In this case, one represents the fact that the materials are in discrete chunks. We retain that part of the model, but instead of randomly placing them in the model, we'll put them on some sort of uniform lattice. So you're getting some of the effect of the heterogeneity, but not the random aspect of it. And I'll show a result from that. I also want to point out that at the November ANS conference, Forrest Brown showed a variation on this lattice method that improves it quite a bit. You can think of it as the spheres are allowed to have some displacement from their equilibrium lattice position. So he'll allow the sphere to be moved in some small distance from the lattice position to simulate the randomness. It's not completely random. You'll see, you would still see some long-range order. So it's not completely random, but it's much better than the rigorous lattice model. Okay, I'm going to talk more about the benchmark method and the stochastic transport equation and the chord length sampling method. Those two methods will be what we will talk about for the rest of this talk. Okay, the benchmark method. again, it's the brute force method. We model a random realization of the random material based on the known mixing statistics of the material. For example, we'll create a rectangle the size of our model, fill that with the matrix material, and then we will pick a location at random, an XYZ location uniformly at random within that rectangular volume, and place one of our spheres there. We'll then pick a second point uniformly at random, and provided that a sphere placed there will not overlap a sphere that's already been placed, we'll put a sphere there. Repeat this process over and over until we've put the required number of spheres in the volume. If a sphere, the placement of a sphere would overlap either the boundary or an existing sphere, we throw away that potential random site and just select another one uniformly. So this way we can construct a random model. We then run a Monte Carlo calculation on that model, and for history number J, we'll obtain an estimate of some reaction rate or leakage or whatever quantity we're interested in, x sub ij. We'll repeat for many realizations and many histories per realization and average the results. So we have to repeat the realizations, that is the construction of the random model, many times, because if we just did it once, we would get a very accurate solution to just one particular random realization, but it wouldn't be representative of any way that all the ways that those spheres could be placed randomly within that rectangular volume. So we need to construct the random model many times and then run the Monte Carlo simulation for many histories on each realization. So clearly that would take a lot of computer time. So I'll show you here, if we average over the histories per realization, we get a result for realization I, and then if we average over all the realizations, we get our grand average, as it were, of our best estimate of the reaction rate for the random system. I should also mention that I don't show the equations here, but we can also use this benchmark method to compute statistical uncertainties like the variance and the confidence intervals. The advantages of this method is it's essentially exact. There are no essential approximations in this method. If we run an infinite number of realizations and an infinite number of histories per realization, we'd get the exact result. It uses established methods. The method of populating the random system with the spheres is a well-established method, and we then just use a standard Monte Carlo technique to solve the transport problem. It has some disadvantages, however. It takes a lot of computer time. We have to run a full Monte Carlo calculation for each realization, and we have to run many realizations. It also can potentially require a lot of memory for mixtures with a lot of spheres. And an example I'll show later, a single pebble bed reactor pebble will have about 10,000 fuel kernels. Each of those fuel kernels might have 5 concentric layers in it, and a pebble bed reactor would have hundreds or thousands of these pebbles. So you can see you would have a lot of geometric regions if you tried to model each kernel and each pebble explicitly, and that's what we're trying to avoid. So back in the late 80s, there was a lot of work looking at the theory of transport through a stochastic media like I'm describing here. And Marv Adams, Ed Larson, and Jerry Pomeranting derived a stochastic transport equation, which I've got shown here on the screen. P sub I is the probability that material I exists at some position R. So in the case of our model, P sub I, or P sub 0, that is the probability that the sphere will be in some position, is essentially the volume fraction of the spheres, and P sub 1, the probability that you're in the matrix material at a given position, is 1 minus that. Psi sub I is the flux, the conditional flux given that a point R is in material I. Sigma sub T of I is just the total cross-section for material I, and so forth. There are some new quantities here, however. Those are these quantities here, the size with the bar over them. And what they are fluxes conditional on a positional point R being on the interface between materials I and J. So psi bar sub I is the angular flux on the interface for neutrons moving from material I to material J. So it represents a loss term for material I. Psi bar sub J is the angular flux for neutrons lying on the interface between material I and J, moving from material J to material I. So it's a source term for material I. And the capital lambdas are just the characteristic lengths in each of the materials. So it's essentially the mean chord length in each of the materials. So we have two of these equations, one from material 0 and one from material 1. Unfortunately, because of these two new unknowns, we have 4 variables and only 2 equations. So we all know that we need more equations in order to close the system and be able to solve this equation. So the point I want to make is that the stochastic transport equation as written is exact, at least for types of random systems we're looking at, but it's not closed. So an approximation is made. A very common approximation is the so-called Livermore approximation. It's interesting because Livermore worked at Livermore. I always found that amusing. And that approximation is just to simply replace everywhere this conditional angular flux appears on the interface by the value of the angular flux within the material, away from the interface, within the bulk of the material. It turns out, even with this approximation, the stochastic transport equation is exact for a particular class of problems: steady state, no scattering, and Markovian mixing statistics. Steady state, that's clear enough. I think it's not a time-dependent calculation. No scattering turns out to be very important, and I'll talk about in that more detail later. But I should explain what the Markovian mixing statistics is. That just means that the random system is such that if you're at a point in space moving in a particular direction, the probability per unit distance moved of going from material I to material J is just a constant. And the probability for per distance moved of going from J to I is also a constant. Okay, a fellow, Sani, in 1989, did something very interesting. He showed that the Livermore model is equivalent to assuming that particle tracks in the mixture are not correlated. And I need to explain what this means. By particle track, I mean the flights of the neutrons between collisions. So every time we go from one scattering collision to another scattering collision, for example, that's a flight. What does it mean that the particle tracks in the mixture are not correlated? Well, if between two collisions, a material crosses a boundary from material I to material J, and then in the next collision goes back in the same direction it came from, it wouldn't see that interface there. So anytime you have a physical situation where what happens to the neutron on a future flight is independent on what happened in the previous flights, then those flights are uncorrelated. Well, clearly, in a real physical system, if you have scattering and a neutron can come back in the same direction it came from, if it saw an interface coming in one direction, that interface better be there when you're going back in the other direction. And in some of the methods, including the one we're looking at today, that's not the case. So it turns out that our method is consistent with the Livermore approximation. Well, I'm getting ahead of myself. So whatever conditions the Livermore approximation is good for, the methods that we're going to look at today are also good for. And well, I've already explained about the scattering, so I won't repeat that. But this will become more clear later, I think. Okay, so here we got the basic algorithm of chord length sampling. We start by selecting a source location, a source energy, and a source direction. We then calculate the distance to the problem boundary, which I call d sub b, the distance to the collision, we sample that based on the mean free path, d sub c, and based on the distribution of distances to changes from one material to the other, we sample a distance to a material interface. And for Markovian material, that distribution for sampling the distance to the material interface is just an exponentially decreasing distribution function. Okay, we choose the smallest of those distances as the event that actually happens to that neutron history. So if the distance to boundary, for example, is smaller than the distance to collision, the neutron is going to hit the problem boundary before it collides, so it leaks. Similarly, if it's smaller than the distance to the material interface, it'll leak before it hits the interface. However, if the distance to the interface was smaller than the distance to the boundary, it'll encounter an interface between the two materials before it hits the boundary, so we do a material interface crossing. And I'll show you that. So based on what happens, either these three possibilities, we determine what happens next as such. If the distance to the boundary was the smallest quantity, then we have a leakage from the problem. If the distance to the collision was the smallest, we do a collision analysis, determine the new energy and direction of the neutron. If the distance to the material interface was the smallest value, then we change from whatever material we're in to the other material. All right, now we're going to see what happens when we try to apply this method of chord length sampling to the problem that we're interested in, a binary stochastic mixture of spheres in a matrix. Well, there's a problem. The distributions of the chord lengths in the matrix material and the spheres are not both Markovian. It turns out, as we'll see, that if we look at just the matrix material, that is well approximated by a Markovian mixing statistics. However, the distribution of chord lengths within a sphere is decidedly non-Markovian. Markovian distribution, for example, you have a non-zero probability of getting any positive distance to an interface. So you can have very large distance to interfaces with non-zero probability. However, with a sphere, the maximum chord length is the diameter of the sphere. So distances greater than that are identically zero, have an identically zero probability. So Markovian mixing statistics are not good within the spheres. Also, with the chord length sampling method, we can't account for the fact that there are hard mixture boundaries. That is, that spheres don't overlap. There's no way to account for that in the chord length sampling method. They don't overlap each other. They don't overlap the boundaries of the problem. So what Tim Donovan did was develop a method called limited chord length sampling as an adaptation of the chord length sampling method to handle this problem. So what's the difference between limited chord length sampling and chord length sampling? Well, let's suppose we have a neutron starting out in the matrix material. We sample the distance to the interface just as we do in normal chord length sampling. So we'll call that d sub I, comma 1. We then sample a chord length in the sphere to fix the position of the sphere. Now, we don't use the Markovian distribution to sample the chord length in the sphere. We actually sample the chord length distribution for spheres, and I'll show you that distribution on the next slide. So we've sampled the position of the distance of the sphere. We place a sphere there, and I'll explain exactly how we decide to orient that sphere on a next slide too. Then what we do is, that's very different from the chord length sampling method, is we use normal Monte Carlo methods to transport the neutron through the sphere. So we've randomly sampled the point where the neutron enters the sphere here, and then we just use normal Monte Carlo methods to calculate the flight of the neutron until it exits the sphere, and then we do another chord length sampling to determine the distance to the next sphere. Here's the chord length distribution. First, I've got one illustrated here for a circle because in some of the earlier work we did things in a 2D planar situation with disks in a plane. But the one that we're really interested in here is the chord length distribution for a sphere, which is just this straight line going up this way. And it's given by this equation. So this is the probability of sampling a chord length of value lambda. Okay, so to figure out where to position the sphere after we've decided the XYZ location where the neutron enters the sphere, we first sample the chord length that we're going of the sphere in the direction of the motion of the neutron. Okay, but that there's an infinite number of points on the surface of the sphere with that chord length. So we need to know then how to orient that sphere with respect to the direction of motion of the neutron and the point where the neutron enters the sphere. And we do that simply by sampling an azimuthal angle uniformly between 0 and 2 pi. Once we've done that, we can then position, we know the position of the center of the sphere, so we just say, all right, there's a sphere here centered at this position, x sub s, y sub s, z sub s. At that point, we do our traditional Monte Carlo calculation of, within the sphere until we get to the exit. At that point, we randomly sample a distance to the next sphere from the matrix chord length distribution, which is given by the Markovian distribution, which is illustrated here. Lambda bar that appears here and here are just the average chord lengths in the matrix material, and I'll explain later how we calculate that. So the graph over there is just a graph of the Markovian distribution. So you can see the behavior I talked about before, that it doesn't go to 0 for large values of the chord length. Before I get into a discussion of how we calculate the mean chord length, I want to show you the test problem that we looked at with MC and P. This is a 25 centimeter sphere containing 781 small spheres. So the matrix material now, instead of being in a rectangular volume, is in a spherical volume. And this spherical volume contains 781 small spheres of 1 centimeter radius, randomly placed within the big sphere. We looked at 2 cases. One with an isotropic source at the origin, an isotropic point source, and the other one with an isotropic source uniformly distributed within the matrix material. In the test problem here, the matrix material, it was nitrogen-14, and the sphere material was boron-10, which is a very strong absorber. We looked, for each of the 2 cases, we looked at 3 subcases of varying optical thicknesses, optical scattering thicknesses for the matrix material of 0.01, 1, and 10. And by optical scattering thickness here, I mean it's the scattering cross-section, macroscopic scattering cross-section of the matrix material times the mean chord length of the matrix material, so the mean distance between spheres, if you will. Okay. Now, I mentioned before that we need to know, in order to construct the Markovian distribution, we need to know what the mean chord length for the matrix material is. And here's how we determine that. We use a Monte Carlo method to determine that as well. it turns out, let's say we consider the origin at the center of the sphere. We want to know what the probability is that a neutron moving outward in a straight line from the origin will make it to the boundary of the sphere without intersecting one of the small spheres inside. So I've shown an example here where it does intersect one of the small spheres, but one can imagine a neutron moving in this direction doesn't intersect the small sphere. So sometimes it will, sometimes it won't. The fraction of times that it doesn't intersect one of the small spheres before it gets to the surface of the big sphere, we call the P0, or the escape probability. And we can calculate that empirically using Monte Carlo. We just draw a number of radii from the center to the outer boundary, uniformly picking outer boundary points at random to determine the radius, and just check to see if we intersected a sphere or not. Then we would regenerate the random model and draw more radii out and average over all these trials to get an estimate of P0. And it turns out, I won't go into the mathematics here, but in some of if you look at the references I'll show you at the end of the talk, you can see where all the mathematics are worked out. There's a relationship between P0 and the mean chord length of the matrix material. So just by inverting that relationship, given P0, we can calculate the mean chord length. So it turns out for this problem, we found that the limited chord length sampling method is 5 to 140 times more efficient than the benchmark method. By more efficient here, I mean it takes that much less computer time for the same statistical uncertainty on your answer. Accuracy was also good for two of the cases. For the two lower matrix optical thicknesses, we got agreement to within 1%. For the more optically thick matrix material, agreement was not acceptable. And this is consistent with what we know about the stochastic transport equation in the Livermore limit. Its accuracy degrades as the matrix scattering increases because this uncorrelated track assumption starts to become more and more important when it's violated. All right, I now want to look, the last thing we're going to look at here is the unit fuel pebble, HTGR unit fuel pebble problem. And here we have a central sphere surrounded by two shells. And this represents one fuel pebble. And the little circles on the inside, and I'll show a blow-up of them on a subsequent slide, are the fuel kernels. So they're the small spheres in our terminology here. And they're placed, in this case, on a lattice. This is taken from a work by Johnson. And again, at the end of the talk, I'll show you some references. If you go to those references, you'll get to the original reference to the work by Johnson. So he decided he wanted to calculate this fuel pebble, but he didn't, and he wanted to represent the fuel kernels within the pebble explicitly, but he didn't use any random algorithm for placing them. He just put them on the lattice and assumed that he would be getting a relatively good solution. So here's what a particular fuel kernel looks like. It's a central sphere of fuel surrounded by 4 concentric shells of various materials, silicon carbide, pyrolytic graphite. These are just the structural material of the kernels. So it's 5 regions total within a cell. So the benchmark problem consisted of one fuel pebble with 9,394 explicit fuel kernels. And if you look, multiply by the the number of regions inside each kernel, you get 47,003 cells total. Actually, I did the arithmetic and I didn't get quite this number, so I'll have to ask Dr. Donovan why they don't agree exactly. But they agree pretty close. But anyway, you've got quite a few cells in your Monte Carlo calculation, and this is just for one pebble in a pebble bed reactor. So the Monte Carlo model for the limited chord length sampling method is much simpler. We have the three concentric regions that represent the fuel pebble, where this gray region in the middle is just the matrix material in which the fuel kernels are placed. And then we have one representative fuel kernel here, which I've blown up over here, outside of the model. It's not physically outside the model. It's in a zero importance region in MC&P terminology. But whenever we jump from the matrix material to the tracking within the fuel kernel, we just call a subroutine that was added to MC&P to jump over into this little, the little sphere and track the neutrons through there. When we exit the little sphere, we track back. We put the neutron back in the matrix material in the large sphere at the point where it left the little sphere. So we have only one explicit fuel kernel represented, and this model has 9 cells total instead of 47,000. So it's a much simpler Monte Carlo model. So here are the results. This is the original result by Johnson, and here Donovan reproduced his calculation just to see that if we could reproduce his result, and also to run more neutron histories than he did. These vertical bars represent the statistical uncertainty. So Johnson's results had very large statistical uncertainties. Donovan ran many more neutron histories and got the uncertainties way down. And we essentially reproduced his result. The benchmark method is all the way on the left, and the results of the limited chord length sampling method are all the way over there on the right. So the limited chord length sampling method agrees with the benchmark results very, very well, much better than the lattice method. I couldn't plot it on this graph because it would have squeezed the top 4 figures together, but down here I have the results of the atomic mix method, which I said at the beginning of the lecture wasn't very good for most applications, and here's an example. We're not even in the same ballpark with the atomic mix method. And as far as efficiency goes, the lattice method was 15 times faster than the benchmark method. So if we're willing to live with this much error for a factor of 15 speed, the lattice method might be a reasonable way to go. It turns out, though, that the limited chord length sampling method is 44 times more efficient than the benchmark method. So it's almost 3 times more efficient than the lattice method and gives a much better answer also. So it's kind of a win-win situation, in this case using the linear chord length or limited chord length sampling method as opposed to the lattice method. So in conclusion, the limited chord length sampling method eliminates some of the problems associated with the regular chord length sampling method for this particular problem. It does that by eliminating the sampling of chord lengths within the spheres and instead doing an analog Monte Carlo calculation within the sphere. Instead of sampling a distance to the boundary, you actually use the real distance to the boundary of the sphere. And it also accounts for the fact that the little spheres can't overlap each other or the problem boundary. And we found, just based on trial and error, that the range of applicability is, this should have a bar over it. This is the average chord length in the matrix. The average chord length in the matrix divided by the macroscopic cross-section of the matrix material. If that's less than or equal to about 2, we get good accuracy. Once it starts to get greater than 2, accuracy of this method starts to degrade. So future work for some future grad student would be to figure out some way to keep the method accurate even for optically thick matrix regions. So I'll finish by showing you some publications that we've written. The first one is a nuclear science and engineering article, and the second one was from a math and computation meeting held very near here just 2 years ago, where there's a lot more detail on the problems that I talked about today and described in that math and computation meeting transactions. And then the last one is a presentation given at the November 2003 A&S meeting that gives a little more detail into some of the things I talked about today. So at this point, I'll ask if there are any questions. Yes, sir.
Why is Capital investigating this type of fuel?
This was Dr. Donovan's thesis work, really. He investigated this problem just because of its general interest to the world right now.
It's nothing to do with Capital.
No, this was, most of our applications are classified, so he couldn't have gotten his thesis so he had to pick something unclassified, and since this was a problem of current interest, that's why he picked it. Yeah. Yes, sir. Yeah.
Okay. Do we have other questions or comments? Yes, Zia?
I have a question. I'm currently doing a criticality safety analysis at Oak Ridge. I'm currently doing a criticality safety analysis at Oak Ridge involving Boral, and one of the problems we're having is Boral's non-homogeneity. Its heterogeneity. Mm-hmm. And one of the main things that we're having is the NRC only lets us use 75% of Boral's theoretical density. Their idea being that somehow the neutron can finagle its way through the matrix without actually interacting with any of the boron. Mm-hmm. My question, I guess, has any of your work shown the major differences in macroscopic absorption cross-section between the heterogeneous model of Boral and a homogeneous solution, atomic solution?
We haven't specifically looked at Boral, but my guess would be based on just these. It's hard to make a connection between, say, eigenvalues and transmission coefficients, but just seeing how poorly the atomic mix model did for the HTGR fuel cell, I would imagine if you looked at transmission or coefficients for a Boral plate or something, it would be similarly bad. Yes, sir.
One
Peter?
little question.
Just a
As
minute,
a
Peter.
preamble. I have one little question. I'm not a Monte Carlo type, but I was wondering, you showed, for instance, Johnson's result, and it was 1.723. And then you showed the error bars. And I was wondering, what's the interpretation of these error bars? Is there a probability associated with that? Does it mean the true value is between?
Yes. Let me look back at my notes here. I believe those error bars were 95% confidence intervals. So what that means, let me see if I shouldn't have done this. Hang on a second. I want to get my, okay, thank you.
You gotta do something to that window up there, like.
Huh?
You gotta X out that thing up there. A little to the right.
Go ahead. Well, while I'm thumbing through here, those error bars mean that there is a 95% probability that the true value, the true Monte Carlo result, would lie in the interval of the error bar. So there's always a 5% probability that the true result would be outside the error bar. So that was part of Donovan's motivation for rerunning the calculation. This error bar was so big that it overlaps the error bars for this calculation and this calculation. So even though one would be suspicious that this value was probably not accurate, one couldn't make a firm statistical assertion that this value is statistically different from this value at the 95% confidence interval. By reducing the error bars, by running more histories, now one can make a stronger assertion that within 95% confidence, this value is different than this value.
Okay, do we have other questions or comments from the audience? Well, then I have a question.
Yes, sir.
Maybe I stepped out for a moment. You might have answered it while I stepped out. But what type computers do you use to run these jobs on? And what is a really long CPU time for the typical design calculation? And what are methods like this? You give us the factor of improvement. So I'm just wondering what's really long that you're trying to avoid and what turnarounds you get with methods like this.
Tim Donovan, if you're in the audience, you could email me that answer. I appreciate it. As I mentioned before, Tim Donovan would do a much better job at giving this presentation. He would do an extremely much better job answering the questions. He ran these calculations either, I think, on a computer at RPI.
PC?
Probably a PC, and I'm not sure what the run times were or even what the machine was. By the time I got the data from him, everything was in terms of figure of merit, which is proportional to 1 over the running time times the variance. So I don't know what the raw data were. I'm sorry.
Well, all right, let me ask a more generic question having to do with typical design calculations at Capitol. What computers do you guys use nowadays? Because I know that a few years ago you used some of the vector machines.
Right.
Do you still use those?
No,
or not?
no. We got rid of our last Cray machines several years ago. In 1988, we got a system based on the wildfire technology. It was originally DEC, then Compaq, and now Hewlett-Packard. You know, those companies have changed hand. This is the so-called Alpha chip. Now that was in 98. So a lot of our Monte Carlo calculations now are still run on that machine. They won't be for much longer because that machine is going to get unplugged soon. It's a 300 and some processor Alpha machine. What we've gone to now is a Beowulf type machines. So we've got the Itanium chip, and one machine has the Intel Itanium chip. The other machine has the Opteron, AMD Opteron.
How many processors?
Less than 1,000,
Okay.
but more than a few hundred. I'm not saying that because I'm just saying that because I don't know.
Okay, that's fine. That's fine. Do we have any other questions or comments from the audience? Well, I hope you've enjoyed the technical nature of this presentation. I have. Since I used to be a neutron chaser, and then I see somebody who still does it, my heart goes pitter-patter because I miss doing it. But we do have a few new faces in the audience, and those new people may not know that we have a reception downstairs and immediately following this presentation, and Dr. Sutton will be down there to answer more questions or to talk one-on-one with anybody that wants to talk with him. But before we adjourn, let's express our appreciation again to Tom for